Jiaqing Bi. I think you're up. Oh yeah, we can see your slide, but I think you're still muted.
Oh yeah, I'm muted. Yeah, can you hear me?
Yes, perfectly.
Okay.
Excellent. Then I quickly make an introduction so we know when to cut the videos. Okay, excellent. Our next speaker is Jiaqing Bi, and she will talk about cuDust. Please go ahead.
Right. Thank you for hosting this event, and I'm Jiaqing Bi. Now, for those who are not familiar with me, I'm now a postdoc at ASIAA in Taiwan, and today I'm going to talk about the code I wrote, which is called cuDust. Well, since this code is generally small scale code, it's more like a toolbox. Today it's more like advertising the science associated with, and instead of advertising a general code like Pluto or Phantom, etc. But overall, the code is called cuDust, but don't be confused with the cuDisk, which was presented yesterday. Well, if you know about the CUDA code, which is the native GPU language, programming language, you see that CU is basically the common prefix for all the codes written in CUDA, and the second half of it means what the code is for. So you see that cuDust is basically for Dust and in proprietary disks. Okay. So what is cuDust? Well, first of all, cuDust is a radiation dynamics code for dust. Well, since it is not radiation hydrodynamics, it means there's no real-time hydrodynamics involved in this code. The main physics involved is the dust dynamics and the radiation pressure from the star and the gas drag from the protoplanetary disk. The code features the ray tracing of the stellar radiation like the cuDisk yesterday, but the difference is that after ray tracing the stellar light, our model does not calculate the reprocessed light within the disk. So the dust just feels the radiation pressure from the star, and that's it. And the code it was used to study the dynamical instability of dust called the irradiation instability, which was published in my 2022 paper with Jeffrey Fong. The irradiation instability is a disk instability happen on the inner edge of the dusty disk. So suppose you have a cavity edge, let's say in a transitional disk. And once the disk edge become dense enough, become optically thick, will become unstable under the radiation pressure from the star. The appearance is that it will become non-axis symmetric and form dust clumps, like the animation shows. The vertical axis is the radius going down, and the horizontal axis is the azimuthal direction. So you see, with time, over time, the disk edge become dense and destabilized by the stellar radiation. But why do we want to, set radiation pressure as the key selling point of this code? Because radiation pressure, again, can potentially open the dust cavities observed in the transitional disk, which we don't know really very much about. Nowadays, gap holding planet seems to be the most favored explanation for those cavities, but there are some problem with it because there are way more transitional disk cavities than large planets observed, even around main sequence stars. So we want to find some alternative explanations for the opening of the transitional disk cavities, and radiation pressure may be one of them. And the radiation pressure also has some other effect, like pushing dust around everywhere, like the pillars of creation on the right. Well, that's typically the result of radiation pressure within that cluster, also with the winds. So again, radiation pressure is not a very new physics. Well, cuDisk yesterday also includes it, and also Phantom and other code. Why do we want to use cuDust? Well, first of all, cuDust has a very important feature which is that it includes the azimuthal direction of the model, which cuDust yesterday doesn't include. And azimuthal direction is the key, is a must-have for triggering the irradiation instability, because the cloud formation due to irradiation instability is due to the amplify over time. The amplify of the density perturbation along the azimuthal direction over time. So if we don't have the azimuthal direction in our model, we don't have irradiation instability. So that's why the cuDust code stand out. But at the current stage, well, you can imagine that Phantom, which is also SPH code, has three-dimensional geometry, and it also has radiation pressure. Why shouldn't we use Phantom? Well, as a render, we technically at this stage we indeed can use Phantom to reproduce the same result. But we except for the efficiency, because the runtime for cuDust is really efficient. So let's say for typically 10, in this model we are using the Lagrangian particles prescription for dust, and in this model we have 10 to the 7 superparticles, which is typically an order of magnitude higher than the typical SPH simulations. And to run for like 500 orbits, we only need half an hour. So that's extremely fast compared with normal, other code. Well, first of all, because we don't have hydro, and second, because it's accelerated by GPUs. And again, let's go to the Lagrangian method for dust. This code is, dust is treated as the superparticles using the Lagrangian method. First, why do we want to do that? Well, first of all, it's impossible to simulate all the dust grains in the disk, which is 10 to the 30 dust grains maybe, and that's computationally impossible. So what we do is we use fewer, like 10 to the 6, 7, 8 superparticles to represent those real dust particles. The good thing about this using Lagrangian method for dust is that it handles dust crossing very well, which is pretty important when the dust grains is relatively large, like Stokes number above 1. But nowadays, people see more and more Eulerian codes, which means the dust is treated as the pressureless fluid, like in the ASIAA++, cuDust yesterday, DustPy, 4CD. These new codes basically use the Eulerian treatment. The key, one of the advantage of Eulerian code is that it handles the it performs very well when the dust particle is very small, very coupled to the gas, which Lagrangian particles treatment doesn't really do well. And in the meantime, it faces the problem with the dust crossing, because when the dust is small, when you involve very small and very large dust particles at the same time, the dust crossing is not very well studied by Eulerian method. So both of the Lagrangian particle and Lagrangian method and Eulerian method have their own advantage and have their problem. So we want to highlight the integration method used in this model, which is called the staggered semi-analytic method, developed by Jeffrey Fong and Drew Muley. The key is that in this model, we are studying Lagrangian particles, but we can reach equally or more accurate solution when the dust particle is very small, with than other methods like written there, first order semi-analytic, second order implicit, iterative semi-analytic, Verlet method, etc. And it preserves the advantage of using Lagrangian particles when the when the particle is large, it remains symplectic and second order accurate. So overall, it handles the dust particles pretty well when the dust particle is small, and it preserves all the advantage that Lagrangian particles have when the dust particle is large. So it is an ideal integration method to use when we want to consider both very large dust grains and very small dust grains at the same time. And for those who don't really know what symplectic means, well, here I show you a example. On the right, on the top, is the sixth order symplectic method solving the Capillary motion. You see that over time the orbit doesn't shift, and the angular momentum variation is basically zero. It doesn't change with the energy variation. With having some fluctuations, but periodic. But if the method is not symplectic, which is, well, one of the example is the fourth order Runge-Kutta method, which is very typical integration method. You see that over time, over a long time, the Capillary orbit shifts. So the result is not accurate. Why? Because the error, well, all the methods have errors, but symplectic method can reserve its error within the same within a certain magnitude, and it doesn't accumulate. But non-symplectic method accumulates its error. So over time, the error goes larger and larger. So the result will shift, which you see from the diagram. The orbit does not overlap over time. And that's a bad thing if you want to simulate dust particles as a very long time range, like billion years, million years, because over time you get wrong results, or worse and worse. So this method treats the long time simulation pretty well. And the next highlight selling point of this code is naturally GPU parallelized by GPU's calculations. Why? Because for dust dynamics and the radiation pressure, dust particles don't necessarily directly talk to each other, which means that they are more or less independent from each other, unless they are indirectly talk to each other via the shadowing effect, but they don't necessarily talk to each other so that they can be parallelized. And when we calculating the density profile in the disk, it can be parallelized by the gray cell, by each gray cell, and they are all independent. The only one non-trivial point is the calculating the radio optical depth, which involves a radio integration. But that can be done with, that can be parallelized with a inner ring from inner to the outer, so expanding ring. So we can still parallelize by the number of cells on the azimuth direction times number of cells on the colatitudinal direction. So overall, it means that all the calculations in the model involved dynamics and ray tracing can be highly parallelized. So that is the natural advantage of using GPUs, and it's very, very efficient. And lastly, we want to talk about the collisional grain growth. That differs from cuDust with some other codes like cuDisk and Phantom, because from my knowledge, Phantom doesn't really handle this very well. When we want to talk about grain growth, in Euler method, we typically talking about solving the Smolakowski coagulation equation. One thing we need to know is that Smolakowski equation is an integral differential equation, which means it is very expensive to solve. And that is why Dust Pi and cuDust are limited to like 1D and 2D, because when we really want to do 3D smaller Kautsky equation, which has a dimension of size beams times the 3D meshes, which will give you a huge 4D grid, and I cannot imagine how large the output file will be, like few giga, one terabytes. So that's basically computationally almost impossible to do that. But for Lagrangian particles, that would be much easier to handle because size is only one property of each dust grains, and adding that into evolution doesn't necessarily involve like doesn't increase the computational cost like what was done for Euler methods. But for Lagrangian particles, if we want to solve the small Kautsky equation, we need to involve some Monte Carlo method, which has been developed a long time ago, like by Zom and Doulemont in 2008. And this method was recently revised by Beutel and Doulemont last year. The key is that the particles collide with particles and they grow. And if we handle this process well enough, we can, this is an analog to integrating the smaller Kautsky equation. So they are basically equivalent. But one thing is that we want to highlight the usage of GPUs, which means we want to parallelize the whole process. But the Monte Carlo method for solving smaller Kautsky equation is a serial process. We cannot parallelize the collision process by like the particles are no longer independent from each other because they need to collide into each other, and that will change their size. But still, technically, it can be parallelized on a lower level. Say particles are not totally independent, but particles far from each other can almost be treated like independent particles because there's a very low chance that they will collide to each other. So it means that we cannot parallelize the collision process on the dust number level. Instead, we want to parallelize the whole collisional process on the grid cell level, which means there is one collision in one grid cell at one time. So that we want to reduce the interference between collision and collision, and we want to increase the parallelization as much as possible. And in this case, another very important question we want to ask is when we are calculating the collision between Lagrangian particles, what is the particle A, and which is the particle B that particle A wants to collide with? This is one of the limitations of doing overall GPU parallelization, because the memory of the device memory of GPU is limited, so we cannot assume that one particle can collide with all the other ones. Instead, we implement that one particle can only collide with one of its k nearest neighbor, with one of its KNN. KNN is a pretty well-studied computational problem, and there is an existing package that is open source third party. It's called cuda-based, and for this cuDust code, we just integrate that package into ours, and we call the functions written in the cuda-based package to efficiently know who are the curious neighbors of a certain particle, so that we know who this particle will possibly collide with. And this is the last slide, and we have a sanity check, because we want to show that parallelizing this meant to be serial process can, well, to some level, can reduce the interference between them while maintaining some efficiency. And here we have 10 million separate particles within a 100 by 100 by 100 cell, and they are uniformly distributed into it. If we do the full serial process, it will be like solving the Smallhouse equation one by one. But here we are parallelizing them on the grid cell, so which means that they are parallelized by by a million instead of by 10 millions. And the result shows that, okay, as long as the collisions do not interfere with each other severely, you can still reproduce the analytical Smallhouse equation solution, which is marked with the lines, and the Lagrangian particles results are shown in the histogram. So they agree with each other still very well. That at least confirms that if we reduce the parallelizability of this model to a certain level, we can reduce the interference and still, parallelize the serial problem pretty well and increase the efficiency. And still, this is still particles directly talking to each particle, so it significantly increased the computational cost. On a conservative level, we can run like 200 orbits within 24 hours with one NVIDIA A100 GPU card. But technically, if we can parallelize using OpenMPI with multiple GPU cards, the efficiency can be boosted by like a few times. So that's all what I have today. I'll be happy to take questions.
Yeah, thank you very much for this very detailed explanation of the numerics of cuDust. Thank you. The talk is open for questions. Yes, Andre has a question.
Hi, thanks for a very nice talk. My question is it possible to include planets in the disk?
Yes, of course. Well, but the problem is the planet does not interact with the gaseous disk, because gas is prescribed or parameterized in this model. As long as you are okay with ignoring that, planet will just be a orbiting source of potential within the disk, and that can be resolved. That can be handled pretty well. And similarly, you can handle like binary stars and multiple stars as long as you can analytically resolve their orbits. That's it.
Okay, thanks a lot.
Are there any other questions? No, this does not seem to be the case. So thank you very much. I think it's time for our break. We are a little bit late, and we have also a slight change of program for after the break. So actually, Thomas Romich is not will not give his talk live. He actually I've posted you the YouTube link to his talk, but he will be available for some Q&A. So in case you want to enjoy the break and watch the video already directly now, you can do this. Otherwise, I suggest we meet in what time is now? In